Estamos en YouTube. Víctor es un alumno de maestría que está pensando dónde hacer el doctorado. ¿Tú estás en la universidad o en el observatorio? Se puede un poco, ya que esperamos 2 minutos, se puede un poco hablar de tu, en inglés, maybe. No sé si Bernardo entiende español, mas vamos a hablar en inglés. So, can you tell us, aquí, interesante. Can you tell us a little bit about your trajectory?
Yeah, so I have a slide for that, just in case. But yeah, so I'm from Argentina. So I can share, but I don't see you, so it's a bit uncomfortable. So yeah, so I'm from Argentina. I did my PhD in Córdoba with Christian Boget in celestial mechanics. And I've been studying stability and architectures of planetary systems. And then I moved to Namur for a postdoc to work with Anne-Sophie Libert. And now I'm in Universidad Católica in Chile. So yeah, so this is my second, well, let's say third postdoc, because before that I did a 1-year postdoc in Argentina with Christian Schupone, and we were studying the natural satellites of giant planets in the solar system. So I've been doing a few different things.
Okay, so I think we can start. 1 second, I was looking, record. So now I will record and then we can start. And so
Yeah,
some
right.
people, a lot of people watch it after it's this recording. Okay, so. So it's a great pleasure to have Carolina with us from the University Pontificia of Chile, of Santiago. And she will talk about the dynamics of a planetary system and understand it's a little bit of a dynamical system and planetary formation.
Yeah.
So it's a very important topic, and we are very happy to have you here. Thank you.
Okay, so thanks, Stefanella, for the invitation. So as she said before, I'll speak about dynamics of planetary system, which is the core of my research for a few years now. So before I begin, I wanted to say that if you have any questions, please feel free to jump in and interrupt me, because it's better to have some kind of interaction. And so I have, as I said, a one-slide presentation of who I am, academically speaking. So I am from Argentina. I did my undergrad in Universidad de La Plata in Buenos Aires. And in 2015, I got my degree, where I studied, so we have a small thesis. And there I studied planetary formation and the delivery of water to the habitable zone. And then I went to Córdoba for my PhD that I finished in 2020. I worked with Christian Boget, and there I changed a little bit and began to study dynamics of planetary system and to try to understand the architecture of planetary system, in particular those systems that are resonant, that are the things that we will discuss during these days. Well, and after that, I went to Belgium for a postdoc, and right now I'm working in Santiago at Universidad Católica de Chile. And here I left my websites, so if you want to contact me or whatever, you have to do it. And so to do these lectures, to organize them, I have used lecture notes both from Christian Boget and Paolo Cincotta, and I used a few classical books in the field that are Murray and Dermot, Morbidelli, and Landau and Lifshitz, and some more new books and papers that will come up during the talk. So before jumping straight to the formalism, the mathematical formalism of the problem, I wanted to present like a historical context of how this field developed and how it ended up being what it is right now. So the most important thing is to say that celestial mechanics is basically uses the principles of celestial mechanics to study the motion of bodies that interact gravitationally, and it began by studying the bodies of the solar system, but right now is a much more complex thing, and it basically tries to solve the embodied problem. So back in the 17th century, the first thing that was discussed were Kepler laws that were basically a geometrical interpretation of the gravitational interaction between two bodies, like a central, the sun and one planet. And it was later on that century that Newton identified the universal gravitational force and was able to provide with a mathematical model to solve analytically the two-body problem. The next century is 18th century. Lagrange, Euler, and many other scientists studied the stability of the bodies in the solar system based on Newton's model to try to explain some variations that they saw in the orbits of the planets. Basically, or the most important thing that they discovered or that they studied was the erratic motion of Uranus. These erratic motions were caused by an undiscovered planet back in the days. And so with this, they were able to predict the position that finally led to the discovery of Neptune. And so based on this method, nowadays people use the same idea to discover planets because of their gravitational interaction. This method is called transit time invariation, or TTVs, and we will discuss that later on maybe tomorrow, well, on Thursday. And so in the 19th century, Heinrich Bruns and Poincaré, they showed that any system with more than two bodies didn't have enough integrals of motion. So basically, the integrals of motions are the solution of the problem, and whatever the system with more than two was not able to be discovered, to be solved. I'm sorry. And so this led to the concept of chaos that is rather simple, and basically they showed that chaos arises from the initial conditions of the system. And so basically, if you have two very, very close initial conditions, you can have very different outcomes for the solution. So the idea is that if a system is chaotic, you will never be able to predict the past or the future of the system with precision. So if you have any slight variation of these initial conditions, you will not be able to know the precise solution. And so chaos is something that appears because of the interaction between different modes of oscillation of the fundamental frequencies of the system. So basically, it appears in multiperiodic systems and is a consequence of the resonances that the system has. All of this we will see in more detail later on. And so, bottom line, every n-body system with more than n bigger than 2 is intrinsically chaotic, and so it's not possible to predict the temporal evolution, but chaos needs some time to manifest itself, and so we can characterize chaos with different times, but the most known or better used is the Lyapunov time, and so before this time appears, so we can treat the system as regular, and if the system is highly chaotic, this Lyapunov time will be small, and so the system will be very unpredictable. However, if the system is well behaved, this Lyapunov time is big enough, and we can think as the system as if it was non-chaotic. And so one example of this well-behaved but chaotic system is the solar system. And finally, in the 20th century, a group of Russian scientists began to study the properties and the effects of chaos, and they began to use toy models to describe the dynamics of n-body system. And the main achievement of this time was the development of n-body codes that were able to compute the precise numerical simulations of the equations of motion without having to do approximations. And so with n-body codes, it's possible to have a precise numerical simulation without computing everything analytically. And the takeaway message of all of this is that computational astronomy is for celestial mechanics as experimental physics is for theoretical physics, because it allows us to predict theories and evaluate models, but the results are only valid for these initial conditions that we chose, because, as I said before, systems that are chaotic have with small difference in the initial conditions can lead to very different results. And so now we can move to the solar system. I'm sorry. Of course, I know you know this. The solar system consists of 8 planets, 4 rocky, 4 giants. From the giants we have 2 gaseous planets, 2 icy planets. Dividing these 2 populations, the rocky and the giants, we have the main belt, the asteroid main belt. We have comets, long and short period comets. We have minor planets that we will see later on what this means. But what I want to say is that we can study the solar system with great amount of details because we know a lot of things about this. And the study of the dynamics and the use of celestial mechanics to study solar system, for example, is that we can try to predict or try to understand things related to formation, for example, and dynamical evolution. And as an example, I wanted to show the inclinations of the planets. So imagine that we have the orbital plane, the plane where the planets are rotating around the sun, is the horizontal line. So you can see that all the planets have different angles. So there is an axial tilt, which is this angle is called the obliquity, and we see that all the planets are spinning with different inclinations in their orbit. And for example, we know that the planets form in a protoplanetary disk, so it's supposed to be a smooth process where we have gas and dust around the star. And so everything is supposed to be homogeneous, and as we can see, this is not the case. And for example, so if this angle is smaller than 90, it means that all the planets are rotating in the same direction. But as you can see, Uranus is almost like laying down. So one thing that we can try to do with dynamics is to try to understand how this happened, how this originated. For example, is there a collision that happened after the formation process that made the planets tilt instead of being like with this angle equal to 0? So these are some kind of studies that we can do with dynamics. Another thing that we can do is, for example, to try to understand the asteroids in the solar system. As I said before, we have the 4 planets, the rocky planets. We have the asteroid belt, and then we have Jupiter, Saturn, Uranus, and Neptune. And so here you see the orbit of Jupiter, and you see that we have 2 groups of asteroids rotating co-orbital with Jupiter. So these are called the Trojans, and they are captured in 2 specific points, which are known as the Lagrange points L4 and L5, and they are in a stable configuration. Oh. Stefanella?
She might have lost the connection, but now she's back.
Okay.
Yes, no worry.
Okay. Okay, so I was saying that so we have these groups of asteroids that are captured in the orbit of Jupiter, and they are co-rotating with it. And then we have the main belt, which is where you can see here the distribution of the asteroids. Here we have the Trojans, and here we have the resonances in the system, and we see that the resonances act in different ways. So, for example, here in the one-to-one resonance, we see that there is an accumulation of material, while in the main belt, we see that the resonance clear gaps, which are known as Kirkwood gaps, and so it's so we can try to understand better the concept of the resonance to try to see whether it will accumulate or clear the material in some specific parts of the of the disk or the phase space. And so to finish up with this timeline, I wanted to mention that in 1995, so 30 years ago, the first exoplanet was discovered around a solar-type star. And right now we have more than 5,000 exoplanets discovered. And so here I show you the distance of the planet to the star and the radius of the planet in the y-axis. And in different colors, you see the mass of the central star. So as you can see, all the colors are around here. So basically, not all, but many of the planets that we observe are orbiting around a solar mass star, so similar to our own. And here I show you different subgroups that we have within the exoplanets. So we have planets that are similar to Jupiter. Jupiter in our solar system, I placed it here, so you can have a clear comparison. So these planets here are called cold Jupiters, and we have the analogous but closer to the central star, which are called the hot Jupiters. We have planets, yeah? Oh, sorry. So we have planets that are similar to our own Earth, but are closer to to their star, which are rocky planets or Earth or super Earth. We have the mini Neptunes, and we have a sub-Jovian desert, but this with the new observations is being populated. So this will stop being a desert soon enough. And so here I superimpose the giant planets in the solar system to show you that there is all the planets that are discovered are very different to the ones that we have in the solar system. So remember that I said that the first exoplanet was discovered in 1995. And so until then, people were proposing formation theories to explain a typical solar system, which was our own. And now we see that our solar system was not at all a typical planetary system. And so formation theories need to be revised in order to describe the populations that we observe. And so I mention all of this because these are the things that we will try to finally cover during these four lectures. I want to discuss some aspects of planetary formation and evolution, but to do that, we have to begin with some things more basic, which are Hamiltonian dynamics, perturbation theory. I will discuss a lot about resonances and the visualization tools that will help us to interpret the numerical results. And I will try to devote the last day to discuss present-day applications to exoplanetary systems. And I will try to show you how we can try to understand the problems that we have nowadays as a consequence of the formation and evolution of the system. So I will begin by discussing Hamiltonian dynamics. I was not sure what was the background, so what things people knew or didn't know. So I wanted to start from the basics so no one got lost. So I'm sorry if it's too basic. But so let's start with Hamiltonian system. So a Hamiltonian is just a function which is used to describe a physical system, generally to describe a system that has some symmetries or is governed by some conservation laws. And usually, so the Hamiltonian encapsulates the information about the energy of the system, the total energy, which is normally the sum of the kinetic part and the potential energy of the system, but you can also incorporate other terms if there is other energy involved. And so a Hamiltonian is a function h, which is a function of generalized coordinates and momenta, coordinates q and momenta p. And a Hamiltonian is governed by the Hamiltonian equations, which are first-order differential equations that allow us to describe the temporal evolution of the variables q and p. And so we will say that we will solve our Hamiltonian system if we are able to have to find all the integrals of motion of the system. So let's say we have a system of ordinary equations where R is a 2n tuple of P and Q, two variables of n components each. So we will have a Hamiltonian of P1 to Pn, Q1 to Qn, and we will be able to write the derivative of P over time as the derivative of the Hamiltonian respect to variable Q, and the same for the other variable. And these equations right here for each of the components from 1 to n are called Hamiltonian equations. So these are the equations that give us the information about the temporal evolution of the variables. And so once we have this, H will be the Hamiltonian of the system, Q are the coordinates, P are the momenta, and these P and Q are conjugate variables which describe the phase space of the system. And so each of these variables, P and Q, have n components, and so these n components are the number of degrees of freedom that a system has. And so, as an example, we can discuss the two-body problem, also known as the Kepler problem, where we will try to, in the two-body problem, we want to describe the motion of a planet around a central object, which is this sun, under their mutual gravitational interaction. And so we can write the Hamiltonian for the system. And once we have the equations, the Hamilton's equations for the system, we can know exactly where the two bodies are in terms of their radial and angular coordinates. So we can predict the position of the planet over time. So one of the advantages of working in the Hamiltonian formalism is that we can apply certain techniques to try to solve or find the equations or the integrals of motion of the system. So let's say we have an n degree of freedom system. So we have our Hamiltonian with our two n components. And the idea is that we will try to reduce the number of degrees of freedom of the system. So meaning we will try to find cyclic variables in order to reduce the number of degrees of freedom of the system, that this will translate into the number of equations of motion that we need to solve. So imagine that we have a cyclic variable, Qn. So this Qn will not appear in our Hamiltonian. So now we have from Q to Qn minus 1 and from P to Pn. And so the Hamiltonian equation for this variable Pn, which is the conjugate momenta for Q, will be this equation here. So as Qn does not appear in the Hamiltonian, this equation is 0, so P is a constant now that we will call alpha. So we can rewrite the Hamiltonian, the original Hamiltonian, from Q to Qn minus 1, and we will write our constant here. And so right now we have n minus 1 degrees of freedom just because we have a cyclic variable. So we were able to reduce 1 degree of freedom, which is the equivalent to reduce the number of degrees of freedom. And so another advantage of working in the Hamiltonian formalism is that if our system does not have cyclic variables, we can generate it, but by changing variables. So in the ideal case, our Hamiltonian is composed by all cyclic variables that will not appear in the Hamiltonian. And so for doing that, this is like a pause to introduce the canonical transformation. So we are allowed to do a canonical transformation if the Hamilton equations are preserved. And so that happens when Hamilton equations are invariant, and that will happen if these two conditions are preserved. So we have if we have a point transformation, then we can write our new set of variables Q and P, capital P and Q, as a function of small p and q, and so the Hamiltonian will be the same, and the Hamilton's equation will be invariant if we if we have a derivative of in time of some arbitrary function. And so so if that happens, the transformation between these two sets of variables is preserved, and we will find a new Hamiltonian k that will depend only on the new variables. And so we can write Hamilton's principle of both the old Hamiltonian in the old variables and the new Hamiltonian in the new variables, and they will be equivalent if the two integrands are the same and might only differ on an arbitrary function f. And so we can solve it, we can do this equality, and if this lambda right here is 1, then the transformation is canonical. And so f, this f right here, will be a function of mixed of the old and the new variables, and this function f is called the generating function of the canonical transformation that will take us from the old set of variables to the new set of variables. And we have different types of generating functions depending on the combination of the variables, but we have their shape here. And we can use it to perform our canonical transformation. And so in that case, solving this equation, we will have that the new Hamiltonian is the old Hamiltonian plus the derivative over time of the generating function. And of course, if this generating function does not depend on time, both Hamiltonians are the same. So basically, we only need to change the variables. So going back to our original problem of trying to find cyclic variables, so we said that we can search a canonical transformation that will take us from the old to the new set of variables such that all our new variables are cyclic. And so if we are able to perform our canonical transformation, the Hamiltonian remains invariant. So this is the equivalent to find a new Hamiltonian that we will be able to write as a function only explicit of the new variable p, capital P. And so if we are able to do that, our Hamilton's equations will be written like this. And so we know that all the p's will be constant and all the q will be written as something like this. And so if we're able to do that, our problem is solved. We are able to have a Hamiltonian that only depends on the new variables, and if we are we can do the inverse transformation and go back to the original set of variables, and we are able to find the temporal evolution of them. And so if this set of variables, in this new set of variables, Q are angles, then the new set PQ are called the action angles variables of the Hamiltonian. And so this is a new post to say, why are these action angles important? Why do we care about the action angle variables? Well, because if we are not able to solve our problem analytically, but we know that our system is periodic, then we are at least able to characterize their motion with this new set of variables. So if we are, so we have basically two different types of periodic motion. We have librations, in which basically in the phase space PQ, the orbit repeats itself after some time t. So we have a closed orbit in the phase space. And we have another type of periodic motion, which is the rotation, in which P is periodic, while Q evolves without bounds. And so we have a system which is evolving, that that repeats itself, but with a translation and after some amount of time t. And so if we are able to find these action angle variables, we know which kind of motion we have, because we have one of the action will be the radius of a circle, and the angle will be varying between 0 and 2 pi. And so that's it. We can describe our system with this pair of action angle variables. And so one way of solving the problem is to find, as we said, all the integrals of motion of the system. So we can make use of what is known as the Hamilton-Jacobi equation, that provides a tool to solve the dynamics of the system. And so to construct this Hamilton-Jacobi equation, we can make use of a Jacobi type generating function, which is basically an S that depends on the new action and the old angles. And of course, as I said before, we want a Hamiltonian that only depends on the actions, so that the problem is solved. And so if we're able to do that, we will be able to solve the problem. And so having the derivatives of the generating function allow us to do this, to write this equation. But solving this equation is not something that we can do so easily, because this is an implicit equation, and unless it's completely separable, it's not usually easy to solve. So we need to go to a different technique to solve this problem, and for that we use perturbation theory. So, as I said before, the Hamilton-Jacobi equation is not typically solved, and not, at least not in the generic case. And so what we will do in the rest of the course is to restrict ourselves into systems that can be written as the sum of two terms. This term right here, which is the unperturbed part or the integrable part of the Hamiltonian, and this term right here, where we have a parameter, a perturbation parameter, which is hopefully small, and we have a perturbation or what we call as well the disturbing function. And these two things right here are many times written as R of the variables and the parameter. So if we are able to write a system like this as an unperturbed part, meaning that we know the integrals of motion of this system, because it does not depend on the angles, then our complete Hamiltonian is quasi-integral. So the whole idea behind perturbation theory is that we will write, if we're able to write our Hamiltonian like this, then this Hamiltonian is also integrable. So in other words, we will assume that there exists a canonical transformation such that we can find a new Hamiltonian that only depends on new actions. And so basically what we will try to understand or quantify is what is the effect of the perturbation on the integrals of motion of the integral part, or under which conditions the integrability is preserved. And so, as before, we perform a canonical transformation, but this time we need to consider that the difference between the old and the new set of variables is of the order of the perturbation. So now the full transformation between the variables will include a term depending on the generating function. So what we can do is to expand the generating function in power series of this parameter epsilon to be able to have an explicit equation for the Hamilton-Jacobi equation. And so the term here with epsilon equal to 0, or epsilon times 0, is the part that corresponds to integrals of motion of h0. And up to order k, we can write the derivatives of the generating function in order to put that in Hamilton-Jacobi equation and have a solution for the problem. And so we will do that by using the von Seipel averaging method. And so we will need to add some things to the perturbation with the complete perturbation. So epsilon multiplied by h1. So we need the perturbation to be periodic, and we need it to be analytic in the variables, and we need it to comply with these conditions here. And for the unperturbed part of the Hamiltonian, we needed not to have essential degeneracies, and we needed for all the frequencies to be different than 0. And so if these conditions are satisfied, we can expand all the Hamiltonian as a power series of the parameter for the perturbation. And then we can group in the exponent of the parameter, and we can replace into the Hamilton-Jacobi equation, and making use of the Poisson brackets, we will be able to find two different equations for order 0 and order k of the small parameter. And the order k is called the homological equation, that only contains all the lower order terms of the generating function. So we can give a shape to this function phi, where so this is the exponent of so the exponential of this exponent that we have here, and so we have the coefficient. So since the perturbation is periodic, is to be periodic, we can express as a Fourier series in the angles, which are expressed here. So we have J, which is an n-dimension index, and this one is the n-dimension vector. And so this is a multiplication of n-dimensional vectors. And so so we can divide this part so we can divide this expression here into a periodic part, which has a mean value equal to 0, which is this part here, that depends on all the angles, and then the homological equation can be written as this part here, where all the parts that depend on the angles are average equal to 0. And so we have this part right here, which are only the purely periodic terms of the homological equation. And so we can rewrite the equations as only the coefficients and only the purely periodic part. Oh, sorry. And we can get the an explicit equation for the generating function, and so we can have our transformation between the old and the new set of variables. But in doing so, we have this term right here, which is this product right here, that we will need to ask it not to be 0, because if not, we will not be able to perform our canonical transformation. And so if we're able to do that, we have our set of action angle variables, and we can interpret what our result will be. And we will be able to go from the old to the new set of variables in order to have the complete solution of the system. And we can get the time evolution of the variables as we have before, but now we have that the difference between the old and the new set of variables is dependent on the perturbation. And so once that happened, so now we can write, we can plot the action over time and the angle over time, and we can see that the mean values here are plotted in red, for example, and we have the variation of the variables respect to the mean value that are dependent on the epsilon parameter. But if we vary the parameter epsilon and we make it smaller, we are able to have much more accordance between the old and the new set of variables. And so we see that we have periodic oscillations around the mean value. And we have, for the angle, we have periodic oscillations around the linear trend defined by the frequency of the unperturbed part of the Hamiltonian. And the amplitude of this variation or the deformation of the variables is of the amplitude of proportional to the perturbation. And so one last thing that I wanted to say before we end up today, because it's almost time, is that it's usual. It's important to understand what the disturbing function means. So imagine that we have a star and we have a planet and we have a small asteroid, and we want to describe the motion of the asteroid in orbit around the star, and we want to know what is the effect of a planet perturbing on the asteroid. And so we want to know what is the effect of M1 on M. And so we have delta. So we have this expression right here in which we have this delta quantity, which is the distance between these two bodies. And so this term right here is accounting for the direct part of the perturbation, which is the interaction between the planet and the asteroid. And we have the indirect part, which is how this planet, which is massive enough, is affecting the star. So it's modifying the reference frame of the system. And so for the disturbing function, it is possible to write an analytical expression to account for all of this, where we will have some function that depends on the ratio of the semi-major axis of both the planets and the asteroid, and also it will depend on the eccentricities. And this angle right here will depend on all the angles of the orbits of both planets. And so these coefficients right here should satisfy the D'Alembert condition, which is that the sum must be equal to 0. And we can, and we know that the lowest order terms are the ones that are larger in magnitude and are those with k equal to 0 and depend on the eccentricities of the bodies. And so, yeah, so for a given specific distance between the bodies, there will be different important terms that will depend on the eccentricities of both the planet and the asteroid. And so, yeah, that's it. I wanted to finish now in order to not to begin with something new because of time. So we have 5 minutes left in case someone wants to ask something.
Okay, so thank you very much for this great lecture. It was I'm sure also the students enjoy all the review. Unfortunately, this kind of material is not always given in classical mechanics course nowadays. Yeah, we discover even like sometimes even like symmetry, integral motion is becoming more optional. So it's great to learn. I mean, for them to review. So let's thank. So open your microphone. So let's thank Carolina, please. Also, they're shy.
Thank you, Carolina.
Thank you.
You're welcome.
Okay, so question from the student. Don't feel shy. They might be shy. So if you can give us send us the slides so they can. Sure. And it would be nice to have some of the references that you mentioned.
Yeah, sure. Yeah, I can give them to you afterwards. Yeah. I need to reorganize some stuff, but yeah, sure.
Yeah, I heard a lot about Pablo Chincota from Simo.
Yeah.
That, like a long-term collaborator. Okay, so next time we will see Carolina on Thursday. And then next week, because we have the Iniciación Científica week, so we will pause and then we'll see Carolina again on the 18th, because we have also a thesis defense on the 16th. So, so we'll be two parts. Okay.
Yeah. So great. See you on Thursday.
Thank you very much again for the great lecture, and see you on Thursday. Bye-bye to everyone. Bye. And Glaston, I guess Glaston stays here.
Okay.
Okay.
I will.
Bye.